hashing and machine learning. So relative to the other lectures, this is primarily about an application of hashing. I was looking through the notes, and I think the kinds of hashing that we use are all covered by previous lectures. But there's a lot of cool applications here, which seem to make a pretty big difference in practice. So I'm going to do a couple demonstrations. If you want to follow along, you can download some source code here. And it seems a little bit loud. Is that too loud? Is that okay? Okay. All right. So you can download the source code here if you happen to want to do that and compile it. And then there's a data set here that you could download and use. I'll be demonstrating things with. Okay, so I'm going to talk about just a very simple version of machine learning, which is just linear learning. So the idea is you have feature vectors, x. You have some label, y. And then your goal is to find some weight vector, w, such that the sum of wi, xi is close to y. Right? I'm going to show you first a simple version of this, which does not use hashing. And then I'll show you a version of it which does use hashing. Okay, so the data set I'm going to talk about is RCV1. This is a document classification data set. It's about 781,000 different lines. So this is 781,000 examples of X, Y pairs. There are 60 million non-zero features. So this is the number of entries in the X vector which are non-zero. And the data set is about 1.1 gigabytes in size. Okay, so the data set itself, let me show you this. So this is the data set. Okay, so what does it mean structure-wise? Yeah?
The slides that you have online, they don't have the Git links.
That's right.
Could you maybe show them again?
Yeah. Here's the Git links. So this actually compiles in both, well, basically everywhere, Linux, Mac, and Windows. I think on Linux it's the easiest, and on Windows it's the hardest. But you can do it anywhere. You have it? Good. Okay, so you have multiple lines. On every line there's a label first, and then you have a set of features. The features are integers and then some dot. Right? So it's a sparse representation of the data set. So this is what a line looks like, and this corresponds to something like 13 is Tuesday, 24 is year, and then these values here, these numbers come from a term frequency inverse document frequency transform, which is a standard way to kind of weight individual words according to how relatively rare they are in the entire set of examples, entire set of documents. So not too important, but now let's try to train it. Okay, so in this particular case, the number of unique features, the number of parameters we're going to be learning is around 50,000, a little bit larger than that. So we can train, and in about 1 second, we can get something with an error rate of 5.13%. Okay, so this is pretty good. If you looked at a traditional statistics handbook, and you said, I want to do ridge regression, which is essentially what's happening here, it would tell you to create a data matrix, which has about 2.5 billion entries, and then invert it in order to find the solution. This solution is essentially the best that's been found anywhere for these features, and we're doing it in 1 second. So we're not doing a matrix inversion, we're doing an online learning. I'll discuss that in a minute. So this is already a very good result and a good approach. If you tried to invert a 2.5 billion entry matrix, it would take you substantially longer. It's actually doable nowadays, but it would take you quite a bit longer. Okay, so this seems all good. It seems like, the problem is solved, takes a second to learn, you get a very good solution. But there's a caveat. The caveat is that doing the TF-IDF transform is actually pretty non-trivial. You have to load the whole data set, you have to do a bunch of counting on it. It's not naturally an online operation like the learning algorithm itself. And so the process of taking the raw data and turning it into a data set that you can learn on in this fashion is the bottleneck, not the learning algorithm itself. The learning algorithm is super fast compared to the pre-processing. I think it's very commonly the case that that's true. That the pre-processing is where the dominant computation is once you move over to good learning algorithms. Okay, so we would like to reduce this cost substantially. We don't want to pay the 2 minutes or whatever it takes to pre-process things. 2 minutes is actually not that bad, but of course we'd like to be able to work on larger data sets as well. Okay, so let's suppose instead we start from the raw data set. So this is the raw data set. It's exactly the same as before, except there's no TF-IDF transform applied. And we have the actual words in the documents being used as features. Right? And now we want to try to learn a good predictor on this data set. Okay, so obviously we need to transform the words into an index somehow to look up a parameter so that we can do the linear representation that we're using before, right? And a natural thing to do, or a natural thing to do, is just use a hash function. So if we do that, we can train. It takes slightly longer. It takes 1.3 seconds. And our error rate is a little bit worse. We get to about 5.76%. So are there questions about this? Yeah?
So when you say you use a hash function,
What's that?
when you say you use a hash function, can you say a bit more about how you're using a hash function?
Yeah, so I was just using a hash function with, in particular I was using remember hash 3 with 24 bits to compute an index, and that index was used to look up a parameter, right? And then that parameter is the one that was tuned for that word whenever that word occurred in the document. Okay, so now if you're a skeptic, particularly if you're a machine learning skeptic, you could say, look, you lost performance here. You lost 0.6% performance. So you might be faster, maybe be 2 orders of magnitude faster, but you lost a lot of performance, and that matters. Yeah?
This is probably embarrassing, but I'm not quite sure what is the problem you're trying to solve.
We're trying to make machine learning fast and easy, basically.
Yeah. So what's the definition of the problem that it solves?
So we're just learning a linear predictor. So we want to find weights such that the sign of sum over I of wi xi is equal to the label. Right? The label is either plus or minus 1. So it's a little bit clearer if I go and look at this one. So we have labels which are plus or minus 1. So we're just trying to do supervised learning. We want to predict 1 bit. Is the document in this category or that category? The truth is that these are actually super categories, so it's like business articles or not business articles. We're just trying to predict, is it a business article or not business article? And we want to use the data we have already observed in order to try to predict, in order to build a good predictor of this. And you can imagine the natural application of this is that you then automate the classification of articles. If you just hash the individual words, then the number of entries that you have after hashing is equal to the number of entries that you have before hashing. Or maybe slightly smaller if you have a collision. Okay, so if you're a skeptic, you're worried about losing 0.6%. But if you're used to hashing, it's very easy to take two hashed values and compute a new hashed value, right? So in particular, what you could do is you could say, I want to have bigrams. Okay, so computing bigrams takes a little bit longer. We're now at 3.5 seconds, and our error rate went down to 5%. So we are doing better now in a time which is substantially less than the 2 minutes plus 1 second that it took to train. Okay. And then, as long as we're having fun, we could say, look, I'm going to create a feature for every pair of adjacent words, but I'm also going to create a feature for every pair of adjacent words with up to 4 skips between them. Right? This is very easy to do with a hash function. And now it's going to take a little bit longer because we have a few more features. It takes 11 seconds. We got down to 4.5% error.
Can you repeat what did you do with this skip for? What's that?
So I'm going to create a new feature
Yes.
for every 2 words,
Yes.
which are less than or equal to 4 apart. So it's like an n-gram with don't cares in between. It's an n-gram with don't cares in between.
Okay.
Right? So there are up to 4 don't cares between the 2 words in our bigram. Okay, so that means that the number of features is about a factor of, well, we computed exactly. There's 344 million features here, and we had 60 million before. So roughly a factor of 5, 6 more. Okay, and then we could also tune the learning rate just a slight bit. The default is 0.5. Turns out that if you use 0.25 in this data set, it ends up working a little better. And now we end up with 4.49%. Okay, so now if you're a skeptic, your argument went against you because we're 0.6% better than we were before. And our training time is like 2 orders of magnitude faster. Or end-to-end running time is 2 orders of magnitude faster. Okay, so this gives you a sense maybe of how hashing can be useful in machine learning. It can make, it really aids the processing of data. And it also frees you up to kind of explore different things, like n-grams and skip-grams and out-of-product features and things like that. Are there questions about this? Yeah?
I still don't understand. So what is actually the input to the machine learning algorithm? So
So the input is, you know, this data set or this data set. Right, so this is a data set. This is supervised information because you have a label.
So this is before hashing. But
This is before hashing.
after hashing, what does it look like?
See, it's a little bit difficult to answer because the hashing is kind of built throughout the algorithm itself. So the way that it operates is there's a parser, which hashes the initial string into some sort of index. And then there's a later stage, which computes the n-grams given the indices. So you're just doing essentially a linear hash on those to compute that n-grams. Yeah?
But where does this input come from? This is obviously not a real text.
Yeah, so this is the rawest available data for this particular data set. What happened to create this was somebody took actual articles on Reuters, and they went through and they had a stop list, so they threw away all the words which they thought were going to be stupid. And then they also, you can see that there's beginnings and endings of words which are missing. So they were trying to stem things, so they had some sort of stemmer program which was running. If I could get a hold of the even rawer data, I would be happy to do that. And I wouldn't be surprised if it actually performed better. This data set was made about 10 years ago. And our learning algorithms, I think, are much better at dealing with the situation where they have a lot more features than they were 10 years ago. Okay, so this is the plan. I was first going to discuss the machine learning just a little bit more to give you a better idea of what's going on. And then discuss how hashing plays with machine learning. And then discuss various applications of hashing, which I found to be very useful. Okay, so the algorithm that we used was not a matrix inversion. Instead, it was online learning. So online learning, I think, is becoming much more popular for obvious reasons. But the basic idea is that we start in some initial state. Maybe it's weights all 0, as it was here. And then you're just going to operate on one example at a time. So you get your example, you make a prediction, you observe some label, and then you compute a loss. In this particular case, we're computing a binary loss. Right? So it's just, did we get the answer correct or wrong, 1 or 0? And then we update the weights. Right? And update rules tend to differ quite a bit from one algorithm to another. A very simple update rule is something that's like this. It's, so you have some learning rate, and you look at y minus y hat times xi to update wi. Okay, so where does that come from? Well, if you have squared loss, if you care about how close y is to y hat squared, you can take the derivative and you can update the negative derivative direction. And that gives you this formula. Okay? So in general, approaches which involve gradient descent, so updating in the negative gradient direction, are very common with online update rules. And then, okay, so this is kind of a picture which gives you an idea of what's going on, but there's a lot of other details that matter in practice. I'll show you what I mean. So if I just wanted to do the update rule that I just showed you, you can see that the error rates are a bit higher. So we end up with 6.5%. Right? So there's a bunch of tricks on top of basic gradient descent, which make a substantial difference in what kind of performance you can actually observe. thing which comes up in machine learning is where did the features come from? There's many different sources of features people use in practice. One very common source is engineered features. So what happens there is you start out with some feature, maybe 2, 3 features, whatever. You see how your system works. You see where it fails. You come up with a new feature, which kind of tells it, the learning algorithm, when it's failing. And then you throw that into your feature set. You just keep repeating this over and over again until you get good performance. Right? So this is kind of a obviously ad hoc process, but I think often real-world machine learning applications work this way. Okay, so this has some advantages and disadvantages. To the extent that a person can understand what a learning algorithm is doing, there's a good understanding of what's going on. And that can be important sometimes, because if you don't understand what's going on, there can be some really obvious failure mode, which is just killing your performance. You always learn the obvious thing. It requires relatively small RAM usage. It tends to be slow at test time, essentially because when humans think about how their algorithm is failing, they come up with ways to express that which are not necessarily computationally easy. Right? And then you have to go through and compute those to get the features to feed into the learning algorithm at test time. Another issue is that this is a very intensive process. So you have relatively low capacity. So the amount of information going into your learning algorithm is small. And that means that if you have a lot of labeled information, you can't really take advantage of it effectively to learn a complex function. Right? And then, of course, it requires a lot of time. Okay, so on these kinds of features, does hatching work? That's a real question. Does hashing work on these kinds of features? Tends to be no. There's several reasons. One reason is your features are dense. They're not like words where they only occur in some documents. Every feature occurs in every example. And that means that the problems with collisions become more important. Right? But there's a more fundamental reason why hashing does not work very well. If you collide 2 different features here, you're erasing information which somebody thought was important to solve the problem. Right? And that's probably going to be a bad idea, because typically people, if you're actually putting in the time to understand your individual features and playing with your algorithm, you don't want to erase that information. It's like throwing away man years of effort. So typically hashing is not useful in these data sets. So there's another approach, which is becoming much more common now. It involves learned features. Okay, so this is the approach to machine learning which won the ImageNet challenge and basically changed the vision community. It's very cool. So the idea here is you're going to have some sort of complex nonlinear system, and you start with very basic observed things like pixels. And then you build up from this more and more complex features until you get to the final solution. Okay, so there's pretty good results for this in speech and vision. It's really dominating solutions to speech and vision these days. It's relatively fast at test time because you choose how to build up features in a manner which is computationally tractable. And that means that whatever solution you eventually get is going to be computationally tractable. And you also have pretty high capacity because you're kind of working from raw inputs. And you can have quite a few raw inputs. It's very slow and painful to train. At Microsoft, there are people who spend weeks training on multiple GPUs to do things. And they need the GPUs, of course, because otherwise it would take months. course, it's relatively difficult because it's not in the exactly how you're going to choose your nonlinear structures are, well, there's a lot of tricks that get used. Yeah?
Can you explain the algorithm again?
Explain.
Can you explain the algorithm of
The algorithm for this?
the slide?
Yeah. So you have raw inputs, like the raw audio signal or the raw pixels, and then you have a bunch of nonlinearities that you train between the raw input and the final output. And each of those nonlinearities you can think of as computing a feature, right? And then you try and get features which altogether result in the last output feature giving you a good prediction. So this is neural networks are the standard name for these things, but generally it's a circuit of some sort where you have a bunch of stacked nonlinearities in order to compute some sort of output, right? And the trick is, how do you actually tune all the parameters of all of the nonlinearities? And that's what takes the days and weeks on the GPU. Okay, so hashing approaches are not very much used here. I don't have a good sense of how useful they could be. I could easily imagine that a hashing approach could collapse. See, one of the problems which can easily happen in these kinds of approaches is that you have too many parameters. And if you used a hash function to collapse the parameters, maybe that would actually be very useful. Because that would reduce your computation perhaps dramatically. But you need to worry about whether you lose performance, and I don't have a good sense of the trade-off there. Hashing is not much used here in practice so far. Okay, so then this is kind of a third regime where learning algorithms are applied, and that's on language-like tasks where you have words. So you should think about things like predicting whether an email is spam, or predicting whether somebody will click on a link in a search result, or predicting whether somebody is interested in a news story. These are all very common word-like prediction problems. Okay, so if you turn words into features, like I did earlier, then you have relatively high capacity. There's a lot of words. You have a fast test time. It's pretty fast to learn. And you have a bit of a problem because the RAM usage can become difficult. And I think that it sort of depends on which scale you're operating at, but maybe on your phone, it might be hard to have a dictionary for every word you encounter. If you're trying to build a spam detector which runs on your phone, or if you're working with big servers which have lots of RAM, you could easily put this dictionary. Maybe you have problems with trying to make a good recommendation of predicting the probability of a click given a query and a result. Right? Because you're operating on the outer product of two sets of words. Okay, so this is really, hashing really helps with these things. It can give you a much faster test time, I think roughly a factor of 10. It can make learning much faster. And of course, it can help reduce the RAM. Okay, so are there questions about the machine learning? Great, so some terminology. A hash function is just something which maps a string into a set of bits, seemingly at random. A hash table, or a dictionary, is something which maps, it has a hash function, but it also has an array, which allows you to check the correctness of any particular hashing, right? perfect hash is a mapping of a fixed, known in advance set of strings to exactly the same number of integers. Okay. So if you're trying to design a learning algorithm, you can use any of those three things. You can use a hash table or a hash function, or you can use a perfect hash. So a perfect hash has an obvious drawback in that you have to know all of your symbols in advance. And that can easily not be true. So for example, if you're doing spam prediction, is this email spam or not? And then you have an adversary that knows if you're using a perfect hash function, they can just come up with symbols that are not in your perfect hash, and then things are not going to work very well. The most common approach in machine learning is to use some sort of dictionary. A dictionary was used to create that first data set that I showed you. Now the disadvantage of a dictionary is that at test time, you have to have the dictionary around so that you can translate the words that you see into individual indexes or indices. Okay, and that means that you have to have quite a bit of RAM to go to the dictionary. The RAM is much larger than the parameters themselves. If you're using a perfect hash, you can use a Bloom filter to at least detect whether or not the thing that you're perfect hashing is actually in the set that you saw in advance. And then you require much less RAM, and things tend to be a bit faster. But still, you require a significant amount of RAM. And now, this picture isn't quite telling you the truth, because the truth is more like you have a fixed amount of RAM. And the question is, how do you choose to allocate your fixed amount of RAM? Right? At any individual time, you're just working with some sort of fixed amount of RAM. Okay, so if you want to do well with a fixed amount of RAM, you want to be able to express as complex a function as possible in your fixed amount of RAM, which means you want to be able to have as many parameters as possible. And now you can see why it's a big advantage to the hash function.
Sorry, what's written black on blue there?
Black on blue, weights.
Okay.
The parameters are often called weights. Okay, so there's a small variation which can be helpful at times. You can unbias things a little bit, and that allows you to sometimes fit a bit more different features into the same RAM budget. Essentially, you can multiply the feature value by a 1-bit hash, minus 1 to a 1-bit hash. So that can be useful. So this means the feature value has expectation 0. That means that when you have collisions, you get less of an adversarial structure. That allows you to tolerate a few more collisions. Yeah?
Why does that improve the collision loss?
Well, it doesn't reduce the number of collisions, but okay, so let's say that we have a feature vector, and we map it via some hash function into a vector space. But we have collisions. That means that entries collide on top of each other. So we could think about taking a dot product between that vector and some other vector in the original space or in the collided space, right? And now the question is, okay, so obviously in the collided space, in the vector space that you map into, it's going to be different. Is this going to be different in a manner which is kind of systematic, or is it going to be just kind of up to the noise in your hash function? Right? So can we make it so that this dot product is an unbiased estimate of the dot product in the original space? In order to do that, you need to have an unbiased, you need to have a signed bit. And the impact of that in practice is it allows you to get away with having fewer parameters while having the same performance. Is that clear? Not quite clear. Okay, so there's a reference at the end which has all the details about this. Okay, so particularly if you're into machine learning, people I think are rather afraid of collisions, and you know that's kind of it is sort of worrisome. So if you have collisions, you're losing information because essentially two different features sort of appear as one feature. So there's several ways to reply to this. One way is to say, look, you really, in these data sets where you're looking at words, it's only a subset of your words which are actually going to matter. So you have a subset of the words which are the important words. And then if you duplicate those important words a few times, it's unlikely that every duplicate will collide with some other important word. Right? And the reason for this is essentially a Bloom filter style of logic. So if you have n important words, and you duplicate them about log n times, and you map that into a hash function with log of n log n bits, then you can arrange things so that every important word has a non-collided entry. And this can be much better than a typical Bloom filter application because I always said important words, and there's many unimportant words. So the raw space that you start from can be much larger than n log n. There's several other ways to think about collisions as well. So think about the span application. If you have a fixed set of parameters, you're going to have to either collide things, or you're going to have to ignore some of your dimensions, right? Which is like colliding everything into a single entry in some sense. So if you are trying to detect whether or not an email is spam, there's a lot of different ways to spell Viagra in a manner which is human recognizable. And that means that if you're using an approach where you kind of map everything not in your dictionary to a single entry, then okay, you're not going to be able to detect and effectively operate against those. So if you have an adversary choosing your features, allowing a random collision pattern tends to be much better than having a systematic collision pattern that the adversary can easily exploit. Yeah?
So how about stuff like Hamming distance or whatever?
How about Hamming distance?
Yeah, like to try to
Hamming distance to try to what?
to detect whether a word is a spam word, to take the Hamming distance to a known spam word, or like Alice was talking about, like similarity is similar to a spam word, then it's probably a spam.
Yeah. So you can certainly do this. So you could build some sort of Hamming distance detector to known spam words. So this would be more of a feature engineering like approach, and it would suffer from the problem of feature engineering like approaches, which is that the computational time tends to blow up, right?
There are not so many words. I mean, spam mails are usually about like 7 total topics. I don't know. I'm just.
So the number of topics, I agree, is relatively small, but the range of ways of expressing those topics is actually much larger than you might imagine.
Interesting.
know about email spam systems that have 20,000 handwritten rules to recognize individual kinds of spam that don't work very well. Okay, there's another objection that comes up pretty commonly, which is that it's incomprehensible. So if you're mapping things through a hash function, maybe it's kind of hard to figure out what an individual index means, right? And this is easily dealt with. So there's kind of two options in VW to deal with this. You can either just, for individual examples, keep track of the mapping from string to index, and then spit out string index pairs for examples. That's what the audit does. Or you can just invert the hash with brute force. But it becomes an option that is computationally intense, but it's not required, which is helpful when you get to the larger data sets. Okay, so this is the basics of why hashing is really helpful. It allows you to use a much larger fraction of your RAM to solve your problem, basically. And of course, it makes things much more efficient computationally. I would mention also, it makes parallelization much easier, which is what was mentioned earlier this morning. Building a dictionary in parallel over many different nodes is actually pretty non-trivial, so you would like to avoid that if you can. Okay, so let's talk about, okay, so obviously you can do hashing on an individual string, right? And that's the simple thing that gives you a baseline hashing your system. But it turns out that once you start having hashing, you want to use it in many different ways. And one obvious way is with these n-grams. So now the question is, how do we compute the hashes for the n-grams? And so an n-gram is, so a bigram, a 2-gram is a feature for every pair of adjacent words, or a feature for every triple of adjacent words, or a feature for every n of adjacent words. Right? Okay, so your input is 2 features, each of which has an index and a feature value. And your output is essentially just a linear hash and then the multiplication of these 2 feature values. Okay, so very simple, simplest possible hash. This is simple enough that you can actually compute these in an online fashion, or an on-demand fashion. So as your learning algorithm looks up an index, you can compute this based upon the other 2 indices. And that's efficient enough as a preferred alternative sometimes. Yeah?
You mentioned that one problem was these adversaries, and then this hatches, it's entirely deterministic. Isn't that then a danger for randomization?
It's a danger. It's not a danger which I think has been realized yet. I think using a randomized hash is a very reasonable thing to do. This is what's being used right now. I think the question is there a sufficiently efficient randomized alternative that in all the cases where you don't have an adversary, you don't mind paying the computational penalty of using it? Come up with one. Tell me one. Okay, so that's n-grams. You can, okay, so that's actually bigrams. You can immediately imagine how to do this for trigrams, or quadgrams, or n-grams in general, right? You just repeat the process with each new word. Okay, so now you want to do outer products. So your input is 2 sets of features, and your output is the outer product of 2 sets of features. This is a really useful primitive for several reasons, but a common one is that you only care about the interaction of two sets of features. So suppose that you wanted to predict which search result should go with a query. Well, you could have query features, and you could have search result features, but if you made something which is linear in these two sets, you would always return the same results for every query. It could not be too effective. Not be competitive at all. So you really want to interact with two sets. And it's in the interaction between two sets of features you start getting some sort of non-trivial performance. Okay, and this is exactly of the same form as before because we're taking a feature from one set, a feature from another set, and now we're creating a new feature. And that means we can use exactly the same approach here. Computing things on the fly to make it efficient enough to use well. Okay, so we can specify I want quadratic features, cubic features very easily. So now let me tell you one application of this outer product operation. So the application is mass personalized spam filtering. So let's say we have 3 million emails which are labeled as spam or not spam. And we have 433,000 users. And we have 40 million unique tokens. Right, so what is a token here? Well, we have some parser that we can run in the email that says, oh, this is a thing. Now the question is, how do you construct a personalized spam filter? So dealing with a 40 million dimensional space is pretty easy. I could easily, let's see, go here. I could change this to be, so that's 24 is 16 million. So I can make this 26, and it will go, right? And then we'll learn essentially the same function as before, slightly better, but not negatively so. So dealing with 40 million dimensional space is very easy, but maybe people have a different taste in what spam is. Maybe some people think that that's spam, and other people think, no, that's important. This is particularly true when you have adversaries that are creating email accounts, right? They intentionally flag emails as spam that are not spam and vice versa, right? So their notion of spam is very different from your notion of spam. Okay, so how do you actually create a personalized spam filter? So let me show you how you don't do it. You don't construct 433,000 different spam filters. It's because the amount of RAM required with the most naive implementation would be about 70 terabytes. This is one for every user times one for every token times 4 bytes per parameter. Yeah?
Why would you need to use all emails for all users?
Yeah, that's true. So you can try to be more clever. How do you want to be more clever?
Cluster users with similar tastes of spam and stuff.
You want to
Cluster different
cluster
users.
the users. Okay, so clustering is always a lot of fun because the quality of your clustering is very strongly dependent upon your metric. So what is your metric going to be?
Tokens of the emails they get, and if it is classified as spam or not spam.
So there's something there what you're saying. I think what you're saying is you want to look at the tokens in the emails that people get and somehow use the label information to control the metric on the that is the right approach, but you're essentially going to end up doing machine learning to do machine learning. Because you're going to have to learn that metric. Other ideas? But you can certainly only represent. See, this is the number of unique tokens across all of those users. Individual users will have fewer unique tokens associated with them. So you can certainly represent their individual parameters more concisely than this, but just keeping track of which tokens occurred with which user. But even so, you're going to use quite a bit of RAM. It'll be less than this, by a couple orders of magnitude, but it'll still be significant. Okay, so now you can try to use hashing. And the idea is that you have the hash of the words themselves. Then you have to have the hash of the words keyed by the user. Right, so for every feature that you had before, you now have two features. One which is the global feature, and the one of which is the per user feature. So this is some words. You have you can think about appending the user ID to the word, and then computing a hash, as well as keeping the original features, and then you just compute your normal dot product. Okay, so now this is very easily implemented if you have this outer product operation, because you can just embed the user ID in a set of features, and you can take the outer product with the original set of features. Okay, and then the question is, does it work? Okay, so here we're using 2 to the 26 parameters, which is 64 million, which is a quarter gigabyte of RAM. It's a lot less than 70 terabytes. It's significantly less than other more clever solutions. And now we can compare two things. You can compare performance of a global, so you can just train on only the global features, and you can ask what kind of performance do you get. And as you increase the hash function to where you have essentially no collisions, you max out your performance at some point. And then you can have the personalized version where your performance gets better and better and better. If it ends up saturating about here, the amount of spam getting through drops by about 1/3. Yeah?
I didn't get. Do you build a classifier for every user, or one classifier then it becomes? Didn't get.
Depends on how you think about it. We're building. You can think about it as a classifier for every user, where the parameters of the classifiers for each user are randomly collided with all the other users' classifiers. Or you can think about it as one classifier where you're computing an outer product on the fly to create the features that you would be plugging into the individual classifiers. You have the original features. You have the features with the user ID appended. You compute a hash for both, and then you just take the dot product. Right?
This looks to me like it's very much analogous to the search, right? Like
To-
to the search problem, like the user, they look at the web page, then so the combination of user and web page is huge, but usually search what they do is they contact features, combining users and features, the dynamic ranking. So there's global ones static ranking, or dynamic
So, going back to the beginning again, when people use machine learning for search engines, typically they use this approach. So they have kind of hand-engineered features which are like, well, what is the similarity between the document and the query? And they have different ways of measuring that, and that gives them different features, and they have ways of kind of measuring how confident they are about individual web pages, and there's a lot of individual handcrafted features which go into these systems. So that's certainly what happens now. You could speculate that there might be some, okay, so the reason why that's what happens now is because people are in a supervised learning paradigm where they have to pay somebody to label things. And because they have to pay somebody to label things, to say, this must go with, this goes with that, you have a severe limit on the amount of labeled information available to you. Right? So then, if you're not limited in the amount of labeled information available, if you're trying to do things from user feedback, like what happens in a spam situation, it becomes much more desirable to have a high capacity predictor. Right? And then this is an easy way to achieve high capacity. Right?
Plus, I guess for search, they're not too much to do with feature learning, because the search world is short, and they don't know the things you can do. That's why they only have about 700,000 features. Now I guess they have much more rich information. So if you learn the action.
Well, if you start using a vocabulary as your features, you start having a lot more room for capacity. Okay, so the approach is clear, right? The approach is clear? Okay. All right, so then we have this personalized spam filter. Now, one thing that you could ask yourself is maybe, different users flag different amounts of email as spam or not, right? Some of them flag no email. Some of them flag a lot of email. Maybe what's happening here is the people have very particular tastes, and for the ones which flag a lot of email as spam, we're doing very well. And for the ones that flag no email as spam in the training set, but maybe at least one test set, obviously, we're doing poorly. Right? It's a danger to consider. Right? And it would make sense to do poorly on the ones that flag no email, because when you go and you compute this dot product here, you're essentially mixing in pure random noise, because you're going to compute a bunch of indices that have never been trained for this user. Right? And this is the danger of collisions. And the answer is that this actually improved the spam catch rate for the users that flag no emails in the training set. There was some effect of this sort, where the users who flagged no emails saw less benefit, but they did see benefit. Why is that? Similar to other users would make great sense if we were using the same index as the other users. But the set of features that we're creating here differ for every user. So the fact that they're similar to other users just isn't being expressed in their feature set. So why does this improve things for the users that flag no emails? So if you did the clustering, then that could be a real effect.
Aren't weights shared?
The weights are shared.
So that would justify it, right?
It certainly creates a channel which allows the possibility that things, but I mean, the weights are shared, but for a user who has no emails, no flagged emails in the training set, because half of their features are just pure random noise that are getting injected, you might expect that it would get a worse performance. Yeah?
Shouldn't they just get the global performance if they don't have anything like you said?
Well, we get the global performance, but maybe worsened by some random noise injected by the additional features which are untrained for them.
We can just ignore that part of it there.
But I mean, okay, so we could keep track of some sort of, did this user flag emails in the past or not? But we didn't here. We just did the obvious dumb thing, and it actually worked better. Yeah?
Is this because most emails are spam, so if you take more emails, you want to get more?
So most emails are spam, that's true. Although there's a caveat, which is that when you build a spam filter in practice, typically it tends to be, there's many layers of rules, where it's more like a decision list like structure, where the non-spam goes all the way down the decision list, but spams get rejected early. So by the time you reach the end state where this classifier would be applied, the ratio is not so clear.
I'm guessing that the false positive rate went down. That's why you have better results. Like not.
False positive rate went down.
Like you would have spammed a lot of you would have marked a lot of emails as spam in the previous
So I should explain the metric a little bit more. Okay, so what's happening here is the people that were working on spam wanted to have a fixed fraction of non-spams be labeled as spams. And then, so you can adjust thresholds on your score in order to achieve that. And then given the adjusted threshold on the score, the question is, what fraction of the spam do you catch? And now, this is when I was at Yahoo, before I was at Microsoft. They didn't want to report actual numbers. So this is relative to the global baseline. So 0.67 means that it's 2/3 better than the global baseline at catching spam after you fix the fraction of false positives. So this is kind of fun. The reason why is because the global predictor that you train when you're doing this mixed training, so you're training essentially a global predictor for X and a personal predictor for XL. They're all mashed together via hash collisions and whatnot, but you can think about them as separate. The one that we're training here is fundamentally different from the one that we trained for the global baseline. And the reason why is because people with very particular notions of what spam are, including spammers, have their particularities absorbed into their personal filter. And that means the global filter becomes pure, it's a better expression of what the best average is across all users. And that means that you actually improve performance. It cancels out the noise effect. Okay, so this is out of products, useful in many other situations as well. And I think that, okay, so this is an extreme example of RAM savings. I think it's very common that when you have these kind of large, throw it against the wall and see what sticks sorts of feature sets, you can get substantial RAM savings by using a hash function. I wanted to show you one other example of using a hash function. So this is polynomial learning. So we're trying to build up a set of monomials from a base set of atomic features in order to learn a more expressive solution, right? So the simple thing that you can do is you can just take the outer product of one set of features with itself, and then you can be linear on that outer product. Or you could work on cubic features. And it turns out that for 30-some different data sets that we were working with, in terms of prediction performance, so lower is better and closer to the y-axis is better. So this is prediction performance, this is training time. In terms of prediction performance, the best solutions actually involved computing a cubic on everything. So that means crossing a feature set with itself with itself. And the disadvantage of that is that the computational time blows up, right? So you end up spending quite a bit more time. So these are quantile. I think this is like the 10th quantile, and the 90th quantile is out here. So there are times when this causes you to spend 100 times more computation, which is painful. So this Apple algorithm is something which runs through the data for a little while. It sees which weights are relatively large. It chooses those weights to create new features involving that index plus the atomic indices. Then it builds up a polynomial over time as it goes. And it turns out that in terms of the time versus quality curve, it seems to get a little bit better. Okay, so this is an algorithm which can be applied at very large scale on like big quick prediction data sets, which people care about quite a bit. And it seems to work and give good performance. Okay, so I'm pretty near done. So when you add hashing in to online learning, you get a lot of nice effects together. Okay, so you have high capacity because we're looking at these word-like features. They're just naturally very many features. You can nail down the correlation effects between individual words. Something I didn't mention earlier, which is often when people are dealing with large data sets, instead of doing machine learning, they just kind of do sort of a correlation count between, and just saying, if I only use this individual feature, what would that tell me about the label? And if you do that for each individual feature, and then you try to combine those results in some sort of systematic way, you can sometimes get pretty good performance, but sometimes not so well. And doing linear learning seems to be tractable in the same sense as counting. Yet it also gets at correlations between individual features, which makes it more powerful. You can have very fast test time. I think when I was first playing around with learning algorithms, I tried using a dictionary, of course. And when I first switched from a dictionary to a hash function, it sped things up by about a factor of 10. Just because the lookup into the dictionary involved destroying my cache, which was not good. You can have very fast learning. I gave some talks there was a New York large-scale learning class that I gave some talks at, which described this in detail. And then the amount of RAM that you use is, it can differ quite a bit data set to data set. There's some data sets where you just can't, the hashing cannot reduce the amount of RAM that you use. There's other data sets where it can be an enormous improvement. Okay, and then the last thing here is, if you have online learning, then you don't need to load your data set to memory. And if you have hashing, then you don't need to have a dictionary which can grow over time as you see more and more examples. That means that the footprint of your learning algorithm is completely controlled. And that's a really nice property for a learning algorithm, because that means that no matter what data set you encounter, Your algorithm is not going to crash. It's not going to go into swapping crazy behavior. It's going to just keep on working. It may not give you the best possible, but it will always do something. Becomes a very reliable and robust learning algorithm. Okay, so there's some references in the notes about uses of the hashing trick and where it's published. This one has the unbiased, the why you want assigned bit in it. This one discusses why it's a Bloom filter-like structure on the important features. And then there's, of course, the local website itself, which has hashing built in. There's actually several other open source machine learning systems which now have hashing built in one way or another. Okay, and then, right, do we want to play soccer? Or we can either play soccer, which I want to do, or we can go through some questions.
One question.
Yeah?
Sorry. So when you hash, you can select the size of the hash, right?
Yeah.
Is this simple truncation?
Yeah.
You truncate the most significant.
Least significant. Least significant bits. And I forced the number of, I only hashed up the number of bits. And being within a factor of 2 is good enough for me, I think. So